So that is the case is to be observed here. So here, if you want to move the test charge from A to B, infinity to desired point here, the distance is small d. What you are moving? A test charge Q naught. How much of the length is to be moved here means dl of length by applying such a force. Okay. So this is also force here. What is the force? Intensity of the line of force of field value F equals to Q naught E. This much of the force which is to be applied to move the test charge in an electric field and against the force of field. Why do you saying against the force of field means here also a test charge is there, due to this downwards is there, against this you are moving the upward direction. That means against the force of field you are moving the test charge by a distance is a dl. So there itself you are doing some work, actional work, that is F dot dl is nothing but a here dw. Getting my point? Where you are doing the work means between the two endpoints A and B. For what purpose? To move the test charge. Okay? Q naught. So that is the case. So in this F dot dl equals to dw, which is nothing but a, you can easily say that F dot dl is FDL cos theta, where theta equals to 180 degrees. Here 180. This is 180 degrees. Okay. So you can substitute FDL cos 180 degrees. That is FDL minus 1. Cos 180 is minus 1. That is a minus F dot DL. Is it okay? So by substituting here, the work done, W value by the external agent to supply this force is nothing but a, that is W equals to F into D. F is nothing but a Q naught E. You can easily substitute it. Q naught E into D. You know pretty well. From this 2.4 equation, WAB by Q naught is nothing but a VB minus VA. So that here you can substitute VB minus VA, which is equals to, that is ED. That means what is the relation between electric potential as well as the electric field? V equals to ED or E equals to V by D. V equals to ED or E equals to V by D. Okay. So here V is the electric potential, where D is the distance between the 2 points where we have been chosen inside the electric field. So that E is the non-electric field. If you want to calculate the electric potential value by using this relation, you can easily calculate. Okay. So this is the one thing here. But here the integral form, that means whenever the field, electric field, which is not in a uniform, means here in different point the field value which may be varies here. So that when the path, that means in which direction the point charge or the test charge which is going to be moving, so that the path of the movement which is from the points, 2 points is chosen here A and B, which is not a straight. The work done can be computed over the infinitesimal small line segments, that is to be denoted here DL here from the figure you can easily estimate. So that the total work done to carry the test charge by this length dl against the force of field in an electric field, which can be given out the integral form, which may be W equals to integral A to B F dot dl. Why? Because of here the work done, which is nothing but a F dot dl. So by integrating the integral, which may gives you here the total work done to carry the test charge against the force of field. So you know pretty well the equation, which is nothing but a W value is nothing but a Q naught into ED. By substituting, you may get the here VB minus VA equals to minus integral E dot dl. Okay. So the negative sign, which is going to be indicating that against the force of field, you are moving the test charge. That is the case. If the point which is chosen, the B point which is at infinity, there itself the electric potential value is zero. By substituting, you may get the only electric potential due to a single point, which is to be considered in an electric field. Okay. So the next one is the potential due to a point charge here. You know pretty well electric field due to a point charge, if it is placed such a distance here, the distance is to be giving out here small r. So there itself the electric field value V equals to 1 by 4 pi epsilon naught Q by R square. Don't be right here R which is related to the electric potential. Here R square which is related to the electric field here. Okay. So the same diagram which is showing here at what distance here. The test charge is there. You can see here, this is the positive charge. Why? Because of here, you can observe the figure here, you can easily estimate that the line of force of field arrow mark which is in outwards. So definitely, uh, immediately you have to imagine that this is a positive charge. Okay. So if the charge is there, there is a line of force of field. If the line of force of field as well as the charge is there, F equals to QE. That means there is an intensity of electric field we are going to be carrying, calculating here. What do you mean by electric field? How much of the effect of the charge which can be occupied by such a region? Then we have to say that that is a electric field value. So in this electric field, if you choose 2 points A and B, which are to be separated by such a distance here, there itself, if you want to bring the test charge, why? Because of we are defining the electric potential V value. So the test charge is Q naught. If you are bringing the test charge in an electric field against the force of field between the 2 points A and B by a length dl, there the force which is equals to Q naught E. Okay. So these arrow marks which is an outward here, these are in inwards means here. Why? Because of here also Q is there, so that these with respect to the test charge here the line of force which is in outwards, so that both the positive charges are there. If you want to move the positive charge, there itself there is a repulsive force which is to be taken place between these two charges. That's what here against this we are moving the test charge by applying such a force. That means indirectly you are doing some external work. Okay. So this R which is indicating the at what distance the test charge is to be placed from the point charge. Okay. You can go for it. Yeah. So from this equation, you can easily calculate that what is the VB minus VA value. 1 by 4 pi epsilon naught into Q by R value. So that if A point which is at a infinity distance, there itself the electric potential VA value should be 0. By substituting, you may get the here V equals to 1 by 4 pi epsilon naught Q by R, not A by R. This is a print mistake. So what is the vector form of the potential, electric potential? Vector form means here, let you consider that what is the relation between the V and E. V equals to line integral minus E dot dl. I will show you. Line integral E dot dl. This is the integral form of the electric potential. Okay. So here dV which is nothing but a minus Ex dx. dl is nothing but idx plus jdy plus k dz. Where E is Ix plus Jy plus Kz. What are Ex, Ey, Ez? Which are the components along the X, Y, Z axis? Okay. So the dot product of the I dot I, J dot J, K dot K, which is equals to 1 here. Remaining I dot J equals to J dot I equals to K dot J. All these which becomes 0. Only 3 components which are to be present here. That's what here you may get the dV value is minus Ex dx plus Ey dy plus Ez dz. Or else you can equate the components to the dV. So which may gives you E equals to minus dou V by dou x. Ey is minus dou u by dou y, Ez is minus dou u by dou z. You know pretty well E is Ix, J by K is Z. And remaining which may gives you, yeah. E value should be like this. That means E equals to minus gradient of potential. Gradient is nothing but I dou by dou x plus dou by dou y plus k dou by dou. This may be written as a del. Okay. Del is an operator which is going to be operated the potential V value. Next is the electric dipole. What do you mean by dipole? Dipole means here which is a two equal and opposite charges. Two equal and opposite charges which are to be separated by such a distance, you may call it as a electric dipole. Somewhat which may have a positive charge and other one is a negative charge which are to be separated by a distance is small r. Then this setup you can call it as a electric dipole. So from the dipole, if you want to calculate the electric field as well as the electric potential V values, how it comes here. So that before that, you have to go for when a dielectric slab. What do you mean by dielectric? Dielectric, which is nothing but an insulating material. So insulating material means here, you need to say that here, insulating material, which is nothing but the resistance of the insulating material, which is high. That means a conductivity of the material, which is very, very less, then you have to say that a insulating material. So that insulating material, which doesn't offer any current through it. So there itself, you need to say that that is a electric dielectric slab. So that whenever you are going to be placing a dielectric slab inside it, then you have to perform that here how the electric dipole which is going to be useful to calculate the electric field as well as the electric potential value. 1 minute. Okay. So here the atoms inside the dielectric which are subjected to be an electrostatic field. So the electrostatic field, the electrons which are inside the dielectric slab, which are to be displaced toward the positive and negative charges. That means positive charges which are resides inside the dielectric slab which are displaced toward the negatively charged plate. Similarly, negative which are displaced toward the positive. So that the strained atom then constitute an electric current. So that the center of gravity of the positive charges as well as the negative charges which are to be balanced here. And if they coincide, the molecule is said to be non-polar. That means within a short distance apart. Then the molecules are said to be a polar molecules. Okay. So water is H2O, hydrogen oxygen molecules, which is a polar molecule, whereas the benzene C6H6, which is a non-polar. Okay. So that in this case, the product of the charges as well as the distance between them, which are to be set like a dipole. Next, intensity of the electric field and electric potential due to a dipole here. You can see what the diagram representing how to calculate the electric dipole. Here is a positive negative charge which is placed at a point A. and the positive charge which is placed at a point B, so that which are to be separated by a distance. What distance and the 2L distance. Okay. So this setup is nothing but electric dipole. Due to this electric dipole, if you want to calculate the electric field value, so that at what point the point is to be denoted here P. So there, uh, here the point B is there. So the body. So that at point B there is a positive charge, at point A there is a negative charge, which are separated by 2L distance here. So the point P which is chosen from the B is at R1 distance, and from point A the point P which is chosen at a distance is R2. So that the center point is O. From the center at what distance the point is to be chosen, at R distance the point is to be chosen. So you need to calculate the capital E value. So first of all, if you want to calculate the two different opposite charges electric dipole value, first individually if you want to calculate the V value, later on you can easily substitute this. So V value which may gives you 1 by 4 pi epsilon naught Q by R1 minus Q by R2. And by drawing two normals on the axis of the dipole here, so that what is that normal here? BM is the one normal, and as well as the AN is also another one. So two triangles are there, right angle triangles are there. That is BOM as well as the AON. So that which are to be making an angle theta with the dipole axis. So there itself you can easily calculate the V value 2QL cos theta by 4 pi epsilon naught R square. But the thing is that here 2Q is the magnitude of the charges between the two uh, dipole here, where L is the here length which are to be separated by two charges. So that the product of the magnitude of the charges to the length which is nothing but a dipole moment which is to be denoted P. Okay. So P equals to 2Q into L. Some textbooks they may be representing each as a 2A into L, whatever it may be here. But the thing is that here according to the definition you need to be denote that here 2Q into L, the product of the magnitude of the charges to the length here, that is nothing but a dipole moment. So in this equation, you can easily substitute in place of 2QL is a P here, P cos theta by 4 pi epsilon naught R square. But you know pretty well here the differential form of the differential relation between the electric field as well as the electric potential. That is E equals to dou V by dou R minus dou V by dou R, not dV by dr, which is a minus dou V by dou R. Partial differentiation. So that you can easily substitute here minus dou V by dou R. You are going to be partially differentiating this value. You may get this. The value is this one. That is a perpendicular direction. What is the E value? And the resultant electric field intensity, which may gives you E equals to square root of ER square plus EP square. There is a small mistakes are there in this textbook. You can go for it. There is a modulus of E which is equals to is there. So here 1 by 4 pi epsilon naught, by substituting these values you may get the E value. V value is P by 4 pi epsilon naught R cube. Similarly electric field value P by 2 pi epsilon naught R. That is the case. Okay, most important question. Next is the torque experienced by a dipole. Torque value. So whenever an electric dipole, like a hydrogen atom is there, H2, okay, which is acted on a uniform electric field intensity capital E, and which is going to be experienced as a couple. Couple means here, which is a torque tau, which is going to be given out here. Torque tau equals to P cross E. The cross product of the P cross E, where P is the dipole moment, where E is the electric field. The cross product of dipole moment as well as the electric field, which may gives you here P E sin theta. So that's what here, where theta is the angle between the dipole to the here electric. Okay, so that where this dipole which is placed inside an electric field, if there is an electric field, there is a line of force of field. If there is a line of force of field is there is a point charge. That point charge is a positive point charge. That means here you need to denote that here the line of force of field direction which is in outward direction. That's what here we have to be denoting. This is a point positive charge. Okay. So if you place this electric dipole in an electric field, from this dipole, if you want to calculate the torque value, the dipole moment. What do you mean by dipole moment? The product of the magnitude of the charges to this distance between them, which may gives you dipole moment. Okay. So you know pretty well E. So cross product is sin theta. That's what you can easily vector notation, which is nothing but a P cross E. Okay. If the angle is P sin theta means next electrostatic generator, which is convinced by Lord Kelvin in 1890. Later on, in 1931, Van de Graaff, which is a device to produce electric potential difference of few million volts. Okay. So it's what is the cheap application in physics is to which is used to the potential difference to accelerate the charged particles. High energy. If more energy, if more acceleration is needed means it may have a high energy. If it is a high energy, then only it may gives you maximum acceleration. Okay. So for this case, what are the charged particles which may require the maximum energy? Betatron. Okay. Electron is also there. It is needed here. When it is going to be using in a betatron, cyclotron, synclocyclotron, all these, if the acceleration is required is more and more, say high energy of the potential is needed here. There itself we are going to be using this. Okay. A beam of energetic particles which are to be made in this way, you can use it in different forms. Atom smashing experiments. What do you say? Atom smashing experiments. So the Van de Graaff generator, which it consists of a hollow large metal sphere, S is there, about to 4.5 meters diameter, which is supported in an insulated column, a belt of some insulating material, like a silk of rubber, which is to be mounted on two pulleys, okay, P1 and P2, which are connected to the electric motor. So this is in detailed diagram, which may have a equipotential sheet, high voltage terminal, positive ion source, and field control rods, insulating belts, positive, all these. Okay, this is the summary. That's the case. Next one is the capacitance. So how do you define the capacitance of a capacitor? So capacitance of the capacitor C equals to Q by V. That means the ratio of the magnitude of the charge to the potential difference between them. So here, whenever you speak about the capacitance of a capacitor, it is needed two plates. One is a positive plate, another one is a negative plate here. Okay. So the thing is that here, when the capacitance of the capacitor which is going to be increased, so when according to the definition of the capacitance of the capacitors, the magnitude of the charge to the potential difference between them, C equals to Q by V. Q which is measured in coulombs, V which is measured in volts. Coulomb per volt is nothing but a farad. Okay. So the symbolic representation which may gives you like this. And the other one is also like this. This is also capacitor. One is a positive plate, another one is a negative plate. But you can go for it. This is positive and this is negative. This is not a capacitor. This is a DC battery. DC. This is a capacitor. This is also a capacitor. Okay, Andy? So C equals to Q by V. Charge which is measured in coulombs. Potential difference which is in volts. Coulomb per volt is nothing but a farad. So capacitor of the capacitance which may be measured in farads here. Suppose if you say microfarad, micro means 10 power minus 6. Picofarad, 10 power minus 12 farad. Like that. The potential of the charged conducting sphere V, which is denoting here 1 by 4 pi epsilon naught into Q by R. And another one is there if you consider the another sphere. That means one is containing a positive, another one is containing a negative charge, which are separated by such a distance. There itself, if you want to calculate the potential as well as the it is required, the capacitance means first of all you should calculate the what is the potential. You know the magnitude of the charge value, the ratio which may gives you the capacitance. That's what here we are first of all we are simply calculating the capacitance value. Okay. So from this you can go for it. C equals to Q by V. Yeah. Units also there. 1 farad equals to 1 coulomb per volt. Okay. So why do we call it farad here? The capacitance of the capacitance of a conductor which is defined as the charge required to raise the potential of the conductor by a unit. MKS units, coulomb per volt. A special unit is there, that is farad, which is used to represent it. It is named in honor of Michael Faraday. Okay. Who is Michael Faraday? Vice versa. That is, if there is an electric field, whenever a current carrying conductor which may produce the magnetic field. If the magnetic field is going to be changes, electric field is also going to be generated. The vice versa formula, which was from the electromagnetic induction. Okay. Line integral E dot dl equals to minus d phi b by dt. That was proposed by the Michael Faraday. On his name only, we are honoring that here. Uh, there is a other contribution which was developed by the concept of the capacitance. So U by V, which is a Farad unit, on his name only. How to calculate the energy stored in a field of a charged capacitor? Right. So the energy of a charged capacitor, which is equals to the work done in charging it. So suppose a potential difference between the plates at any instant of the time is V, then the work done is dW. If it is bringing in a small charge dQ to the capacitor, the potential V is given by dW equals to VdQ. Uh, the total work done in charging the capacitor plates, W equals to VdQ. There itself, if you substitute, V value is a Q by C. That may be by integration of x dx, which means nothing but x square by 2. So you should have half cv square value. But only the thing is that here how the energy which can be stored in a capacitor, in which form the capacitor of the capacitance is going to be stored. That should be in the form of potential energy. Okay, in the form of potential energy. Wait a minute. So the capacitance of the capacitor can, how the energy which is stored in a in which form the energy can be stored. The energy which can be stored in the form of potential energy. Okay, this is important bit here, objective bit. In the form of potential energy, the charge can be accumulated on the plates of the capacitor. If the charge, uh, which is when the capacitance of the capacitor is going to be increases, when the plates of the capacitor which is going to be offering more charge, okay, so then the capacitance is going to be increased. But the by the definition itself, C equals to Q by V. The thing is that here the potential difference between the plates which is going to be decreases, the capacitance of the capacitor is going to be increased. So that if the capacitance of the capacitor is going to be increases means here it is going to be accumulates the more charge. It can be stores the more charge on it. That is the case. Okay. So, ఇక్కడ reading level stuff. Next is the combination of the capacitor. When the capacitor which are to be connected in a parallel, there itself the potential difference which is remains same. The thing is that here the charge which can be varied. If the charge is going to be varying, the potential is same, the capacitance is also going to be different. So in this case, if it is connected in parallel, the capacitance of the capacitor C equals to C1 plus C2 and so on. Or else if the capacitors are going to be connected in series, there itself the charge remains same, but the potential difference between the plates of the capacitor is going to be changes. So that there is a V1 plus V2 plus V3 and so on. And the capacitor of the capacitance is also going to be changes. So in this condition, C equals to 1 by C equals to 1 by C1 plus 1 by C2 plus 1 by C3. This is in parallel condition, series condition. Okay. Next, capacitance of a conductor. Isolated sphere. Isolated means only one single sphere is there. If the capacitance of the sphere radius is smaller, there itself the capacitance is nothing but a in this. Two concentric spheres are there. Two concentric sphere means the radius. First capacitor radius is small a and other one is the small b. So by these two, if you want to calculate the capacitance, there itself, what is that? You have to imagine a Gaussian surface. So it comes here a Gaussian surface, which is in the form of a spherical nature. There itself, if you choose a point on the Gaussian surface, if you calculated the electric potential value, V value, so that by integrating that, you can get the entire value. That is the case. V equals to 1 by 4 pi epsilon naught into Q by 4 pi epsilon naught K. 1 by A minus 1 by B. Later on, you may get 4 pi epsilon naught K V by B minus C. The thing is that here we are calculating C equals to Q by V. In that potential value calculating, there itself, if you substituted the V value by simplifying it, you are getting a C value, capacitance. Next, cylindrical condition. So, cylindrical means this one. Inner radius of the sphere H is cylinder, which is a negative charge. Outer one is a positive charge, which are separated by a distance here. First one radius is small a and other outside one is the small b. So there itself a dotted line which is representing here a Gaussian surface. The arrow marks which is in inward, you can see here from positive to negative arrow marks. Getting my point? Okay. Actually, this one, the original thing, Gaussian surface, calculated the V value, immediately substituting, you may get the 2 pi epsilon naught K log B by. Next, cylindrical sliding. Next is a parallel plate condenser. Parallel plate condenser means this one. A and B are the two plates of the capacitor which are parallel to each other here, which is having such a area is area of cross section is capital A, and one plate is containing a positive charge, another plate which is containing a negative charge, which are to be separated by a distance small d. There itself, if you want to calculate the capacitance of the parallel plate capacitor, first we are calculating the E equals to V by D or V equals to ED. Based on that, if you substitute it in the equation of the capacitance of the capacitor, Q by V, you may get epsilon naught A by D. Okay. What is epsilon naught? Epsilon naught is the permittivity. A is the area of cross section of the plates, where D is the separation between the two plates. The thing is that when you place a dielectric slab between the plates of the capacitor, if you place, what is going to be happen between the plates and how the capacitance is going to be changes. Between the plates of the capacitor, if you substituted here, you can see here a dielectric slab thickness is small t. See this thickness is small t. Which one is the dielectric slab? This one is the dielectric slab. Dielectric material means which is an insulating material. There is no conductivity should take place through this material. Okay. But inside there is a Induced charge carrier. There is a induced charge carriers are there. But here the surface charge density. What is sigma? Surface charge density. That means here a plus. This is a negative charge which are separated by a distance small d. The thing is that when you introduce a thickness of the small t of a dielectric slab which is introduced between them, then here negative charges which are attracted toward the positive plate and the positive charge which is attracted toward the negative plate of the capacitor. So what is the total distance between them? D minus T, which may gives you. What is the distance? That is the case. D minus T. Okay, epsilon naught A by D minus T. Capacitance of the parallel plate capacitor when you introduce a dielectric slab. This is a variable condenser. The series of plates, the stack to form a condenser, which is called variable condenser. Okay. This will be a one set of plates will be fixed and which is called stator, like this, and second set is a rotor. Such type of condensers which are used very much in various electrical fields of electronics. Whenever the variation of the capacity leads to change in the frequencies needed. That means in radio communications, televisions, etc. Next is the fixed condenser, God ring standard condenser. Force between the plates of the charged condenser. Force value. F. Mechanical force of attraction per unit area between the inside the surface of the each plate, which is equals to the outward electric pressure over a unit area of the charger. Okay. So that should be equals to F equals to sigma square by 2 epsilon naught K. When the potential difference between the plates remains same, in this the both plates are connected and the two ends of the battery, one is a one end is to A and other end is to B. Then the force is Q square by 2K epsilon naught A square. By doing it, you may get the here. Here also with respect to this half epsilon naught A square. Energy stored in a capacitor. Sigma square by 2K epsilon naught. Okay. So by tomorrow's class, we will discuss about this remaining portion. We can go for the DEP relations. DEP means displacement current, electric field, polarization. All these three we will discuss in tomorrow's class. Right. Thank you.